And here's an example. The single degree of freedom system is subjected to a force whose spectral density, SDOF, okay, so of a force, say, plus omega minus omega of S is equal to S naught. So it's a constant term. It's a value, a certain value, S naught, okay. Find the complex frequency response function of the system, the power spectral density of the response, and the mean square of the response. And so this system looks like this, okay. It's a mass spring damper system. I've got a force that's being input. I've been given the PSD as the force, and I've got to find my various terms in terms of X. Okay, I've got to find the, it says there, I've got to find the complex frequency response, the power spectral density of the response, and the mean square value of the response. So, complex frequency response, okay, so there's my input, like I said, it's a constant force. There's my equation of motion, okay, that should be straightforward. You should understand that if you've got a mass spring damper system, then you've got that equation of motion. That's pretty basic. And obviously, if you go through the process of replacing X with X, big X, e to the j omega t, and so on, you end up guessing this is your frequency, complex frequency response. So there's our complex frequency response, that's part A. Part B, we need to find the power spectral density of the output. Well, we know the output, which is X, is going to be the magnitude of the complex frequency response squared times by the frequency response to the input. Okay, so obviously I've got this term here, times by S of 0 gives me my output. Okay. Now to find the expected value, there should be an equal sign here for the eagle-eyed among you. Okay, apologies about that. Make a note of that. Equals. The expected value, so the mean square value of the expected value of the square, or the mean square value, we know is the integral of your output power spectral density. Okay, so you take your input, the input power spectral density multiplied by your frequency response function, okay, and you get your output. And so obviously S naught is a constant, so that can come outside the integral. We do the integral of this, and like I said, what we use is we use that identity that I've given you, where we had, you know, the B naught plus B1, yeah, and so on, and you can work it out, and you end up getting this as your term. And so, and yeah, like I said, you can do some simplification and stuff. You end up getting pi times S naught divided by Kc is your expected, your mean square value. You take the square root of this, okay, you'll end up getting the RMS. Now, how did I go from this line to this line? Well, like I said, I use that identity. Okay, so there's my identity, and in this case, if you go back to the equation, you can see that on the numerator I've got 1. So that means that up here I've got B1 must therefore be 0. Okay, and B0 must therefore be 1. And on the bottom I've got minus m omega squared. So my coefficient for the omega squared is minus m. My coefficient for j omega is c, and my coefficient for the term without any omegas on the end is k. And so I've got, so like I said, omega squared is minus m. Okay, so over here I've got minus a2 omega squared, so that must be m. A2 must be m. My j omega I had c, okay, and my one without anything was k. So a0 must be k, a1 must be c, and a2 must be m. Like I said, b0 is 1, and b1 is 0. You get those terms, and hence you find the solution. We have b0, which is 1, divided by, so 1 squared divided by a0, which was k. So 1 divided by k times by a2, which is m. So we've got m over k plus b1 squared, which is 0. And then on the bottom, we've got c times by m. And if you do like I said, if you go through the process, so that's my term. 1 over k times by m plus 0 over cm. Obviously, what happens is the m's will cancel out, and I get 1 over ck there times by s0 pi, which is where that comes from. So like I said, that's a useful identity to know. But like I said, it's on your equation sheet, so you can use that if you need to. Let's see. It's on the first page of the equation sheet.